Okay, so maybe we start. Okay, I don't know how many people will enter afterwards, but so let us start. Just before the talk of Johannes, just wanted to say this is a very informal presentation of what this AI Initiative for Science is going to be. We are like presenting this more formally on the 25th of November. I mean, 2 weeks from now, where there is a conference, etc. So we will like make a very short presentation of our platform. This, but just to say, this is just a group of so we with Veronica Sanz and Jose Enrique Garcia and myself, we are trying to make this platform of interest in machine learning applications to science mainly and other areas. And we are trying to have a common ground for events like this one, and so for interests and for interaction, of course. But yeah, so we will talk more about that on 2 weeks from now. And for a moment, we have the pleasure to have Johannes here with us, talking about analyzing art with artificial intelligence. So Johannes, thanks.
Thank you. Hi, hello. Well, welcome first. The initial title was AI for art in general. It included paintings and music, but I've decided to focus only on paintings for today. So I call it part 1 in case there's someday a part 2. The reason is I've been told to start at an introductory level. So I'll make an effort to be pedagogical, to introduce a lot of concepts about neural networks. So hopefully if you don't know that, you'll find it useful. If you know it already, I apologize. Please wait for the new stuff at the end. Find the mouse here. All right, so this is work I've done here at IFIC Universidad de Valencia with Gabriel Barenboim, Veronica Sanz, and also with our master student, Gabriel, who's here in the room. And the question we started with essentially is one that many people have, many physicists ask us is, how do neural networks work? How do they learn? What do they do? Because one thing that people seem to not like, physicists anyway, is the idea that they are black boxes. Now, we can talk about this for a long time. I use lots of black boxes. I use my brain, it's a black box. I use my car, it's a black box. I understand the principles, the same way I understand the principles of how a neural network works. But still, if you think about it, we do use them a bit as black boxes. The idea still is that we want to understand a bit more, and that's perfectly fine. I'm also very interested in understanding more and more about them. And so we want to ask questions. First, I have to find my mouse. Was the first step to ask questions? Yeah. And the way we ask them is try to open this black box. So we all agree that we don't like a pure black box that does things without us understanding anything. We want to understand more about it. So let's open the black box. And that's a bit the idea. A bit cumbersome. I'm just going to move here. Sorry about that. Okay. And what we'll do is we'll look at neural networks and we'll peel the layers, a bit like an onion if you want. And I'll introduce the idea of layers of a neural network for those who don't know about it. And we'll look at it layer by layer. So we look inside the box, the black, supposed to be black box, at the different layers. Now, another thing physicists often do is rely on symmetries to simplify problems. And so one of the questions we had is, well, rather than using neural networks as black boxes, let's study them as physicists do. So we can study lots of systems, complex systems in physics and other sciences, in biology, where we can consider neural networks an object of study for physics. Okay, so let's take it this way. Let's open them and look how they work. And the question is, do they analyze problems a bit the way we do? Do they identify symmetries? Do they use them even? They might identify symmetries but not use them. We give a neural network or machine learning a task to learn, a machine learning algorithm task. They learn it. They might identify the symmetry, but they might not use it, or they might use it. And how do you find out? How do you extract this information from them? So the idea is if we figure this out, we gain some understanding of how they actually work. So it's a long summary. The introduction would be to define a bit what all these terms I've started using: artificial intelligence, machine learning, deep learning. Then I will focus on neural networks and I will introduce many of the concepts. And finally, starting from the third part here, I will talk about, I will deal with the research we did, which is to look inside on the black box, different layers of the neural network, at how it handles a problem that has a symmetry. That we know has a symmetry, but we don't tell the neural network. Then we'll try to apply this not to physics problems potential, but to paintings. So in part 4, there'll be an extra work to do, extra effort to do to be able to do that. And then in number 5, we'll find out if it works or not. But you can probably guess, if I'm giving the talk, we get some interesting results. And later we'll talk about applications and extensions, some of which Gabriel is working on, our master's student. Okay, so first some definitions. I'll start with a Venn diagram, if you want, of AI. I'll compare machine learning with traditional programming, and I'll motivate then the architecture of neural networks, why you would want to build that. So the Venn diagram is this. In the public sphere, I guess, if people talk about AI or are scared of it, is because they think of something very general and very powerful and completely autonomous agent, a robot that can do pretty much any task on its own and replaces human. Okay, that's wonderful. We're not yet there. Well, I don't know if that's wonderful. I think Brian is doing So it's a powerful concept. We're not yet there, obviously. That's what I mean. So most of the time, people talk more about a specific or narrow AI. So it's a program, maybe it could be a robot or whatever other agent, that performs specific tasks, but responds to the environment. Okay. But not all the tasks that a human can do, like make jokes, make sandwiches, a specific one, recognizing images or computing something. Now, within AI, the way it is implemented most of the time is something called machine learning. So it's a whole range, a very, very wide range of algorithms which learn from data. And the important point is without explicitly being coded, meaning they're coded explicitly to learn from data, but they're not coded. It's not hard coded in the algorithm what to do in each specific case. You don't tell the algorithm, if you encounter this, do that. If you encounter if that, not this. It's more, if you want some meta algorithm that you program, you program an algorithm for the algorithm to learn then on its own. We'll talk more about it later if it's not clear. Now, within this class of algorithms that learn from data without being explicitly coded at each step, there's neural networks here at the bottom, so a smaller range even, that are a specific class of machine learning algorithms. And they're made of layers of so-called neurons. And the more layers, the deeper they are, the more they are called deep neural networks, and it's called deep learning. The advantage is that they're very versatile, and that they can be made arbitrarily fit, and they can handle very large amounts of data. So in this sense, they're more general than other machine learning models. But on specific tasks, they might not be better. So they're not the solution to everything. So these are the ones we'll talk about. Yeah. Okay. Now, because again, I've been asked to start at an introductory level and be as pedagogical as I could, I found the best way was to use animations. And there's this wonderful YouTube channel that I'm going to rely on. And I'm going to start with a very standard problem, just called a digit recognition problem. So imagine you're given, somebody has compiled 60,000, I think, examples of handwritten digits, and then taken digital pictures of them. So there are 28 by 28 pictures, 28 by 28 pixels. And then each pixel encodes the value, the intensity of the light there from 0 to 1 or 0 to 255, whatever you want. And now the task, what we want to do is give this matrix of numbers, this array of numbers to a computer and have it tell us, well, this is a 3, obviously. It's obvious to you, but it's not obvious to the computer until you figure out how to code that. So we want it to not say 0, not say 8, but 3 for this one. Now, if you think about it for a minute, how would you program that? I think it would be logical for most people to think, well, I know that a 9, even though people write it differently, has definite shapes. It usually has a circle at the top and a bar at the right. Now, there's variations on how you write them. Same for the 8, it's usually a circle on top of another, or a circular shape, defined loosely. 4, we might have a problem. Not everybody does therefore the same way. But we could consider a couple of styles of drawing the number for the digits for. So you could say, well, I'm going to look at your image, at your matrix of pixel intensities, and I'm going to look for circles, look for bars, and if I find enough in the right places, I know it's this digit or that digit. That's perfectly logical. And then you need to figure out how do you recognize these shapes. Well, image processing has been around for a long time, and we know how to do that. We use what's called a kernel or a filter. So you convolute your image by another matrix of the same size if you want. So you multiply the activation or the intensity of each pixel by a specific array of numbers that you choose. And you then perform a convolution. If you want, it's a discretized convolution interval. You multiply each pixel here by the value here, and then you sum. So it's a discrete convolution interval. And so what you do is you choose your filter. Here, I'm showing a filter that happens to be a horizontal bar. And when it's laying on top of the top bar of the 7, then the multiplication will give you a large number. You can go a bit further and not just look for high intensity somewhere, but gradients or steps, edges, contours. And that's what this shows. That's why here there's two colors. There's red and there's green. So depending on how much the intensity changes at the top of the bar of the 7, if you do this multiplication by some negative numbers in the black, some positive numbers in the white, then you get an even higher and higher number. So you're detecting a gradient, a strong gradient, or an edge. So we can do that. It's all known. And if you apply it, let's say, to an image of this line, you get this kind of result. So you get edges that are present in the picture. So you can imagine now that if you apply this to the digits, you will find shapes, you will find lines and probably circles, and you can build more and more complex objects and then recognize them. It might be hard, I'm not saying it's easy, I've never done it, but conceptually, it is feasible. But it gets more complicated if you ask about other tasks. Because in the case of the digits, we know there's 10 different digits, and we know there's simple rules for what they should look like. Now, the next example I took is this. So this, I found it very interesting. This would be really hard to code, you know? How do you recognize the chihuahuas from the muffins? If you apply the same if-then standard programming logic, you would look for round shapes, which you can do. There'll probably be eyes. Look for shapes that are not quite round, but have these two holes. It might be a nose. And you put a threshold in which you decide this is an eye, this is a nose. Compute their relative distances. Count how many there are. There's too many eyes and noses. It's either a muffin with lots of blueberries, or it is more than one chihuahua, and you have to decide what to do. If you compute the distances, maybe you figure out that the image is flipped, so you have to turn it around to get the nose at the bottom, etc. And then at some point you decide, okay, if it's not a chihuahua, then it must be a muffin. This might be feasible. Again, I haven't done it, but you can see where this is going. It's getting more and more complicated for something that your brain does quite well, although sometimes it's a bit hard. I think some examples here really would think that these are eyes. So now, obviously, this is going to break down at some point. For instance, if I show you these images, these are dogs, all dogs, and if their task is to recognize the different races, breeds of dogs, with these blurry pictures, with different lighting conditions, some dogs are half in the shade, different orientations, some dogs are running away from you, like this one at the bottom right. Lots of different backgrounds that you'd have to remove. You'd have to even identify which part is the dog and which part is the background. You can't do it with color here. You see that you have to hard code explicitly an incredible number of if-then conditions in the standard programming. So you see that this is going to break down. This approach will not work. Each time you will have to redo the whole thing again, and it will get more and more complicated. So what you probably want to do at some point is say, well, this was very nice, finding these kernels, these filters, and getting the right ones to extract the information I want. But at some point, I'd like to automatize this, not code a filter for eyes, for noses, for tails, but make it automatic. Can I ask my software to try all combinations of filters in all the places in the picture figure out itself what is the best combination to actually tell me the answer. And this is a bit what we want to do. We don't want to code every detail of where to look at what, but just say, find the best combinations. And so that's a bit the idea. Rather than specifying, I'm going to put this initial convolution kernel here, bar, looking for a horizontal bar, like at the top of the 7, just try everything and tell me which one works best to find 7. I tell you which ones were actually 7, which ones were 3, and then you decide where you should have placed this. Okay? And then we'll use it for something else. Or you tell me which one differentiates better between dogs and muffins. So that's a bit the idea. And one good way to do it is by building this architecture of neural networks. So I'm going to describe it a bit and then talk about cost functions and gradient descent. So if you represent neural networks as graphs, usually represent the neurons as circles. So they have an activation, they hold a value if you want. Where in the input here, it was the intensity of each pixel, but then it's just the value that some function has calculated. And then you represent lines, which are represent the free parameters to compute other values of other activation of other neurons. This sounds more complicated than it should be. Let me play this. So you see that here is 784 different values that are bright or black are the intensities of the 28 by 28 pixels. If I join them together, the little a's, these are the values, and I multiply them by parameters w that are called weights. And I sum, this is exactly the convolution I was mentioning at the beginning. You get the multiplication of your image by another matrix that should appear here that has all these different possible green and red numbers, either positive or negative. And one instance of all these possible kernels is this horizontal bar that would detect a horizontal bar here at the center. Okay, so one way to represent everything I said before is just this. You take all the values of the input pixels, multiply them by the value of these lines, symbolized by the color, sum that, and that's your discrete integral convolution. And you get a result, which gives you the activation of that neuron, depending on the activation of all these input neurons of your pixels, in function of all these weights. Now we have to decide which values we put in this matrix, which weights W we choose. And before doing it, just one question. For the moment, I'm just trying to make something very complicated that is actually just a linear fit. So we're not going to get very far with this. And we need one crucial ingredient, and that's non-linearity. Because now if I start building more and more complicated versions of this, as long as it's linear, it will remain linear. So I'm doing something very complicated for just a linear fit of many variables. That's it. So what we need is a function called activation function. When I do this sum, I do not pass just the sum. I then pass it into a function, sigmoid. So I take this matrix multiplication of the weights by the activations of the previous neurons or the pixel, and then I compute, I just apply a function to it. So sigmoid is a classic example. We like it because it has an interpretation in terms of statistical physics or thermodynamics. But actually, computationally, it's cheaper to use ReLU, which is rectified linear unit. So it's constant equal to 0 when the input is negative, and identity when the input is positive. The reason is that the derivative of that is very simple to compute. 0 on the left, 1 on the right. And that's a very useful property. But the important thing is that it's a nonlinear function. People have invented tons of them. Some work better in some cases. It doesn't really matter. We introduce this nonlinearity, and it's really crucial. Once we have that, then we can start thinking of doing this convolution several times, building layers. If you like. I take the initial pixels, I do this convolution, add the nonlinearity, get a result. I will put this inside a neuron, so it's a number. And then I can do that repeatedly. And the more times I do it, the more layers of neurons I add, the more complexity I can get, because now it's nonlinear. If it was linear, there's no point in adding more and more. So if this works, we would hope that as we add more and more layers, so we take the initial 28 by 28 pixels, perform this convolution and nonlinearity, we get results here. And the number of neurons is unimportant here. We could try, I don't know if there's 12 or whatever, we could try a different number. And then we take these and we apply the same logic, again, a convolution if you want, integral, and compute the values for these. And then finally, at some point, we decide, well, we need to decide which of the 10 digits we're seeing. So one way to do it is to have 10 different neurons and hope that neuron 0 will fire when we see the digit 0, hope that neuron 1 fires when we see digit 1, and none of the others fire, or very little. Now, it's just a hope at this stage. The idea is that because we've built this non-linearity, at every stage, we hopefully have, there's a chance that if we do things right, this neuron fires when it's seeing a shape, okay? And at the later stages, at further and further layers, deeper and deeper into the network, it fires when it sees a more complex shape, so a higher level feature. I'm not proving anything of that. That's the hope. Now let's see what we can do. So we start with random weights at the beginning, because remember we want to scan over all the possible combinations of parameters. So we start with a random weights, we compute, and we get a result. This is obviously digit 3. Here in example, we show that, well, digit neuron 3 fired, but also 4 and mostly 8. So the network is unsure whether it's a 3 or an 8. Whereas ideally, we would have wanted, essentially neuron 3 to be nearly the only one to find. So because we initiated this with random weights, we get rubbish. Now, we can still define a cost of how far we are from the target. Okay? Because if you think about it, I said before, we're going to do this randomly, and then we can try all possible convolutions, all possible weights. We probably don't really want to do that, because this would take a very long time. So I'm building a neural network, even just this one that we showed has thousands of parameters. So we have to scan thousands and thousands of parameters over the whole space of real numbers. So finding the best values, the best combination will take a long time. So we don't really want to do that. The problem is we start from a random value of this set of parameters, of these weights, and we want to find a better one. So what do? If we put garbage in, we get garbage out. And as this cartoon says, what we need is just to change the numbers a bit, probably, right? Except we just don't just change them completely randomly. We need to know in which direction we change them. That's the trick. So we know how to do that. We stir it with a guide. We define a cost function. You probably got the idea from what I showed before. When we initialize this at random, then instead of having 1 for the output of neuron 3 and 0 everywhere else, we got some numbers. We take the difference between what we got and what we wanted, square it, so it's all positive, add all that. That's how far we are of the proper prediction, of the ideal prediction for digit 3. Then we do it for all the other images of digit 3. We average that. And we do it for all the digits we have, 0, 1, 2, 3, etc. And we average that. And that's our average error. We just want to drive this down to minimize that. And so we know how to do that. We perform gradient descent. So we look at the cost function as a function of the weights, which are variables that we can change freely. And whenever we get a result, we take a derivative with respect to these weights, and we change the weights by doing some step in the direction of the opposite of the gradient. Now, the size of this step, all of this, there are lots, it's an art, even more than a science, I would say. There's lots of ways to do it, to optimize it in different cases. I will not get into that. But at least we understand that we have to go in that direction. Now, the size of the step is not obvious. I'm saying that the compute the cost, then the gradient with respect to the weights, then you go in the direction of lowering negativity of the gradient. So this is illustrated here. In case it's not very clear yet, you just compute the cost, extract the gradient, and then you nudge the weights by a small amount, and you go over and over and over and over. And at some point, hopefully, you get a better result. Your cost should be going down. Okay. This was a lot about introductory neural networks. And obviously, I've skipped over a lot of things, but some of it is very important for what we're going to do. So now, going back to the problem I mentioned before, which is to see how a neural network handles a problem that has a symmetry, for which we don't tell it about the symmetry. We don't tell it to use this symmetry. We want to see if it does and if we can follow what happens. So I'm going to define a decoy task. So a task we invent about a problem with asymmetry, and it's going to be a supervised task, which we know about. Then we'll perform some dimensional reduction, and I'll have a look at the different layers, at what happens through the different layers of the neural network. So the task is simple. We make up a 2D potential, and to make the problem very simple, we draw its contour line. So we compute isopotentials, if you want, equipotentials, and we draw them in black over a white background, or we just build a table with them, where for every pair X and Y, every pair of coordinates of 2D, we say whether the point is on a contour line or off the contour line. Now we can do many versions of that. This is the simplest one, or the one with the least information. Either you want a contour or not. We could label the contour by value or by altitude. So 1, 2, 3, etc. sequentially. Or we could do a bit what Gabriel has been doing, which is instead of doing a discrete classification of contours, do a regression of the value of the contour. But right now, I'm just showing the simplest thing. Then we feed this information to a neural network with a number of layers and neurons per layer. It turns out to be 10 and 200 for what we chose for speed. And we train it. So as time passes, it learns the potential, and at some point, it knows it. Meaning, we gave it data of points in a 2D plane, some of which are in the light colored the background, if you want, are not on a contour line, and some darker ones were on a contour line. It took 100 epochs for it to learn. Epochs, if you want, is the number of time I go through this algorithm of gradient descent. I'm skipping about the batches and everything, but it tells you how many times I go through this with some factor. So at some point, which takes about a minute on a laptop for a few thousand points, the neural network has learned to reproduce that potential. Fine. But what does it actually learn? What's it learned is we've given it these red points, which we say are part of the class on a contour line. So we've broadened the contour line, so it's more than a pixel wide. I'm going to zoom in. Yeah. So we've got the red dots here. You can't really see the colors very well. So it's wider than 1 pixel, wider than 1 point. We've spread a bit the contour to help it. And we've got this, those that are supposed to be blue are purple here. And so these ones are not on a contour. Now you learn a function to predict that. I give them to you and you learn and you build your function that flips from positive to negative here on this, you figure out where to put the line, which function to build. It has to flip from white to black, depending on whether we're closer to the contour or whether we're off the contour. So you see, this example is actually maybe doesn't have all the information I want to show. Maybe here, right? This is a proper fit, I'll say, because the neural network makes mistakes sometimes. Here, it flips sign on the wrong side of these 2 points and these 2. So it makes some errors. It hasn't learned the problem perfectly. Here, I think in this example, it gets every point exactly right. So it's memorized every single point. And that's actually a problem, because to do that, it invents a complicated function with lots of like peninsula, if you want here. Like these 2 bits that want to reach each other. These are features that don't exist in the data. It's because there's a gap. I've sampled randomly the purple points from the black background. And see the gap here, and it's invented that maybe these could be touching each other. Here, none of that happens. Here we have smoother separation between the contour and the background, and that's all good. Here it's building these complex things, and it sees arbitrary artifacts like a little patch of white here. So we would predict a spot here to be on the contour, and that's wrong. It's overfit. This is a classic problem that's standard in machine learning, in neural networks in particular, and it's known how to solve it. It's important here because if I symbolize what I've just been showing, let's say I want to build a separation between the purple, should be blue, but purple points and the red points here. If I generate them by hand with a random algorithm, and I put the real separation being the black line, and then I generate some noise, some fluctuations around that, I will get sometimes these errors, a point on the wrong side. Now, if I fit an algorithm for too long, I get this overfit line. The separation that the algorithm will invent will be this green line, maybe, where it gets every single point right, but this is actually wrong. Because if I do the same manipulation again, I generate again at random, different random seed, I will get different points. And then the better predictor will be the simpler version, the simpler black curve that has a simple parameterization, whereas the green curve that is all wiggly and very complex will make more errors. We just learned this instance of the noise perfectly. That's not what we want. And you see in particular that if I'm looking for symmetries, I probably trust this black smooth curve better than the green one. And if I look at the green one, I'm not going to find a symmetry. Okay, so the way to deal with this is, again, I'm emphasizing this because I've been asked to talk about introductory concepts. So if this is obvious to you, you take the data you had at the beginning and you split it into two parts. One, the test set that you never use in the training, and the other one you call training set, which you actually use in the algorithm. So you feed it to the neural network, you do this training, this gradient descent, and as time goes by, as the number of epochs or training step increase, you reduce the error on your training set. It should go down forever. It should never really go up much. It might stop going down. But at some point, from time to time, you check how well you're doing on the test set that the algorithm has never seen. And there, at the beginning, everything seems to go well normally. It is learning it better and better. But at some point, it will stop improving and will start making more mistakes. That's fine. That's the moment where your algorithm is starting to go from the black curve to the green curve. So you want to stop training there. Training more would be a mistake. Okay, so it's called early stopping, early termination. So it's all standard. Now the question is, that really interested us is, how did this happen? How did the neural network learn? Because I showed you a little animation of the predictions it gets through time. But now let's look in the layers. So I told you before, there's 10 layers of neurons. So it's quite deep network with 200 neurons in each layer. So we can look at the values, if you want, the activations of all the neurons in each of the layers. Now that's 200 coordinates. So for each point in the data set, that was in 2D, now it's in 200 dimensions. So we need to project that onto 2 dimensions, and the simplest way is using PCA. So that's partial component analysis. So you take essentially a 200 by 200 correlation matrix, diagonalize that, and you look at the combinations, so linear combinations of the original 200 dimensions. Now the largest variance, so where the data is actually spread. That's an example in 2D. You would look at the axis here where there's more spread in the data. That's linear, very basic, but it will be enough. We also looked at more complex ways of doing this, but there's no. Now, I'm going to show examples, and to see a bit more, instead of the simple yes-no contours of before, I'm going to give them numbers, so colors if you want. The bottom of the potential is the black, then I go through the colors of the rainbow all the way up to red and even grayish. Yeah. So these are contours, instead of being just contour 1 and background 0, is 0, 1, 2, 3, 4, 5, 6. So I have a whole range, so you can see better what happens. But it's essentially the same problem. So this is the projection in 2D after each of the layers, or in each of the layers. The initial layer is essentially the image itself. So it's a kind of distorted square image, where here I fed it a translation invariant potential. So you have straight lines. And the color of the line tells you, if you see at the bottom of this black square, it says class 3. So it's a contour line of level 3. Here class 2, here 1. So the contour lines go up as I go through the rainbow. Okay. So they are straight lines. I fed it the translation invariant problem. And that's just the image. Now, after already one layer, it's done something. It's reduced the distance between different points on the same orbit, or the same contour line. It's shrunk the contour lines if you want. So it's starting to identify all these points together. And then beyond that, it's also starting to fold the whole thing over itself. So like a paper, if you want, folding it along the vertical line here, if you will. So it's identifying that this contour line numbers, class number 7, has to be identified with this one. So it is using the symmetry. And more than just the translation, it's identified different contours that have the same value. And at the end, take this example I put here. I didn't choose a particularly good example where it doesn't actually shrink everything to points, but let's look at the next example. Another potential, this one circular rotation invariant. So you see how it extrudes it, and then it aligns the contour lines vertically, and then it starts shrinking the distance between, you see these 4 points? Oh, I missed one. These are the 4 extremes here, 1, 2, 3, 4. So this class is cut in the image. You don't have the whole circle, you just have these points. And they're put aligned against along the vertical again, and then shrunk together, collapse onto 1 point. You can see here the same 4 points. And here, I guess you can see, well, they're still separate somehow, but they're closer and closer together. And each class, each contour line has been shrunk to points. It's identified all the points on the same one. So it's clearly using the symmetry more and more as we go deeper into the neural net. That's another example. Again, I think the best is to follow the bottom of the potential, so these 4 points. See how it aligns things vertically, then collapses these 3 points here together into 1 here. Okay, so we did this, and once we had that, we realized, okay, it seems that it's working. Something is happening here, where the neural net not only finds the symmetry, but uses it layer after layer. We can see how what it does seems to respect our intuition of what we want it to do. It's folding things over and identifying points that are related by symmetry. And the question of how we can extract this info, well, it's kind of clear now because we've already used the info from each layer and projected it onto the dimension. So we're going to do the same. We're focusing on the last layer where the information, again, as we expected before, has been extracted to a higher and higher degree of abstraction. So it's collapsed all the orbits onto 1 point, or nearly. So it's the layer where the information is the clearest. So where it's used the symmetry the most. So here the same network is represented with the entry at the top and the head at the bottom, if you want. We read the last layer, project onto 2 dimensions with PCA, and then we get a drawing. That's the kind of drawing you get with just the 2-class problem. It's like a boomerang. And there's a color red for this. This must be the background, or this must be points on the contour, and this must be points in the background that are, I don't know, blue, I guess. Okay. So that's what we did on potentials. We were confident that we were seeing something, but we wanted to apply it to something a bit more difficult. Because if we work on potentials and apply it to potentials, it was working. Now we want to apply the same to R. So to do the parallel, I'm using again this potential. And if I show a Kandinsky painting, you can see the parallel obviously. So we just have to find a way to process these images in a way that is compatible with what we did here. What I mean is we want to use the same algorithm from beginning to end on both physics potentials and images. So we need to find a way to process these and to extract the simplest sketch you could draw. If you were to describe this drawing to someone and draw it without even colors, what kind of lines would you represent it? So do a quick sketch on an outline of it. So this is again some image processing. We do need to redefine the problem, and I'm just going to show what we do. We take paintings and we turn them into outlines. This is Van Gogh's Starry Night in grayscale or orange scale, so in intensity only. I focus on the moon here. So there's the moon surrounded by the halo. And because it's Van Gogh, we know that we probably, not just for Van Gogh, but for others as well, probably want to lose a bit of detail. There's too much information for us to work with in the original picture, especially for Van Gogh, right? So we want to blur things a bit. We still get the main shapes, but we lose a lot of the details. Then we do what I said at the beginning, the extracting contours or edges. So we extract the edges here with standard image processing techniques that we discussed at the beginning, and we get these contour lines, so the edges of objects. And we want to train essentially the network to predict background for everything that is blue and contour for everything that is yellow. There is 0 here and 1 here, or 255. To help it a little bit, we're going to essentially blur things a bit again. So we're going to spread a little bit the contours to be a bit wider than 1 pixel. And we're going to introduce a no man's land between the background and the contour so that the network doesn't try to predict anything in the red here. Just predicts, we just train it on points that are either in the yellow or in the blue. We don't feed it any points that is in the red. So we give it this space where it does whatever it wants to switch from 0 to 1. And we don't ask questions what happens in between, just to make it a little bit easier. Okay, so we go back. Now we've defined the pipeline for the image processing. We've defined it looking at paintings. We're going to apply exactly the same to the potentials, thousands of potentials. And for each potential, we train one neural network of the shape I mentioned before, 10 layers of 200 neurons. And so we train those. And here's the result. I don't know where it's moved up, but here's one potential. And here's, for that exact same potential, I don't know, 6 or 8, I guess, different PCAs. So it's not different potentials with rotation invariance. It's I trained a network 8 times or 10, whatever, on exactly the same potential. But since I initialized the network with random inputs, it ends up in a slightly different place at the end of the training, right? And not just because of this, but because the whole procedure has some randomness. So it turns out that when I do the PCA, I don't get the same image. And by this, there are some cases where it seems I just get a flip of directions or swap X and Y. That's one thing. But even then, there are some that are different. This one and this one. I don't see the relation between these two PCAs of exactly the same potential. In fact, I see as much variation horizontally for this exact same potential as I see vertically between potentials of different symmetries. Except maybe these ones, these are the potentials without any symmetry. They tend to have more fuzzy PCAs. So maybe that I can see by eye. The rest seems very hard. Except somebody sees something. So you have to remember that we don't have to do this by hand or by eye. We can use, you guessed it probably, the Chihuahua versus nothing. So we build a classifier for these PCAs. And we ask classifier, can you distinguish PCAs from a problem that was originally symmetric, even though I didn't tell you it was? Or can you distinguish PCAs of potentials that were originally rotation invariant? And so we do that. But first, I want to recap a bit because I've already talked about a lot of things. We're going to use convolutional neural networks. But first, again, what we did, we defined potentials. So this example is a rotation invariant potential. So from this, we build a decoy problem or image, if you want, so a 2D problem where we have to predict black and white in this image, essentially. Except that we actually process things a little bit before, just to be able to apply the same to paintings that would be more complicated images. We simplify the images in this image processing. And we feed it to this neural network, train it to learn to reproduce that image, essentially, or that information. Read the last layer, project it onto 2 dimensions, the simplest way we can think of, PCA. And then we ask, can you distinguish this? Can you tell me if this came from a rotation invariant problem, or from a translation invariant problem, or from a reflection invariant? Okay, so since these are 2D images, which is not by chance, we did this on purpose, we're going to train a neural network that is specialized in recognizing images. And these type of networks are called convolutional neural networks. And I have to introduce a distinction that I haven't made until now. I've been talking about convolution kernels, even though I was actually describing dense neural networks or fully connected neural networks. So these are networks where all the neurons in one layer depend on all the neurons in the previous layer. Priorly you do this, there's nothing against it. It can enable you to build as much complexity as you want. But if you look at an image, you probably don't want to do this. Because when you try all these kernels, all these convolution filters, you probably end up looking at objects that are more like this, that are local. You probably don't want to combine the value of the pixel here with the value of the pixel there. If you're looking for a dog, here there will be some background, and here another bit of background, the sky, a cloud, and here some grass. They have nothing to do with each other. There's no logical reason to expect them to be important combinations. Mostly, when you look for features, even shapes of digits, these are all local. You're asking if locally there's a horizontal shape like this, or a circle. So you probably want to build local kernels that have a small size, maybe like this bar. And then not only that, you want to stand them all over the image, the exact same kernel. So rather than building huge kernels that cover the entire image and that are as complicated as you want, you build small kernels with few parameters, and you scan the same kernel over the whole image. So there's much fewer parameters. So you take into account the fact that your image has probably local features that are important, and that the correlation between very distant features is not so important. But you also take into account the fact that it's translation. Your problem is translation invariant. If you look for a 7, if the person has drawn a 7 towards the top left of the image or the bottom right, it's still a 7. You don't really care where the 7 is. You're looking for it all over. So that's why you're going to move this kernel, this horizontal bar, let's say, all over the image. The point is, there's much fewer parameters in this. So you take advantage of properties of the problem that allow you to simplify and to be much more efficient. Now, there's a second step we use. Oh, no, first, okay, this is how it would work. Let's say the blue is your image, and then you multiply by these numbers in red. You multiply each time a kernel that is 3 by 3 here. That's the yellow part of the image, and then you get the convoluted result. So you scan, move your kernel around the image, so the same kernel, and multiply locally the small size, not the whole size of the image. Now we use a second trick, transfer learning. So instead of building our own convolutional network from scratch, which would work, but would take us more effort, we use one that experts have trained over millions of images. So huge network that people have trained to recognize cats and tables and cars in images, and train over millions of images to get a very good accuracy. We're going to use this network, part of it, on our new data set that is different, that is these PCA images, these boomerang shapes. And the difference is we need to change the output. We need to change what's called the head of the neural network. Instead of predicting 40 different categories of objects, table, baseball bat, or glass, we ask to predict translation invariant, rotation invariant, so 5 different classes. So that's the blue. We changed this bit that has the last layers of the network, but the architecture is the same, is unchanged. Even the parameters of the model, or the weights, we start with the same values as here. Then we train to improve for our exact problem. We still do some training. Okay, this is depicted here. What we're doing is we've collected all these PCA, so these 2D images of things we've extracted from inside the neural net, and each has a label that is, this is a PCA from a problem that was actually translation invariant. This is a PCA from a problem that was actually rotation invariant. Can you figure it out? Can you recognize that? Can you see the parallel, the difference between these two and the parallel between this one and this one if they're both translation invariant? And well, you can probably guess. Can the CNN tell me the symmetry of the original problem just from the PCA? If I'm here, it's probably because the answer is yes. Otherwise, I would be talking about something else. The question is how well. So we do 5 classes: reflection, continuous translation, discrete translation, or periodic potential, rotation invariant, and no symmetry that we know of, or a weird shape. Now, by pure chance, we would expect to get it right 20% of the time, but doing this, we get it 73% of the time. So nothing incredibly amazing, but you have to realize that we've thrown a lot of information. We just drew contour lines with either black or white instead of having the whole range of the values of the potential, and we've projected 200 dimensions onto just 2 using PCA. So we've just done the simplest thing we could think of. Now we train the same, that was on potentials. Now we train the same network on paintings. That's the Kandinsky of before, and that's the Bangkok Starry Night. So you see very, very dirty versions of sketches that simplify the image. There's a church here, that's the moon, and the halo around. So can it find symmetries in it? Hopefully here we would find some discrete translations of periodic potential. And this is the result. So yes, for the Kandinsky, we find to the high degree of precision discrete translation, right? Apparently, maybe to some degree, the network might even think that there might be some rotation. I guess that's for each circular piece of the image. But yeah, I wouldn't necessarily trust that. It's a very low level of probability. Now for Escher drawings, there's a lot of translation, discrete again, some reflection, which is obvious here as well, Mondrian as well. This Mio painting has more reflection symmetry. It's actually supposed to be a person, and indeed there's an axis of symmetry here. This fractal has also a mixture. So to some degree, it might be that there's no symmetry at all, says the neural net. For the case of Pollock, we all agree there's very little symmetry or none at all here. The network agrees. And here, it's another Van Gogh, and here there's a discrete translation. I guess it's the pattern of vertical reflections here that are kind of regularly spaced. And as Picasso, obviously, this for any cubist paintings, it will usually find that because there's repeated shapes, repeated patterns with a standard size, it will usually say there's some degree, it looks like there might be some discrete translation. So if you want, that's kind of an intuitive definition of symmetry. It doesn't know about composition. It doesn't know that if I do two reflections, I get a rotation. It says, well, this looks a little, says what you would, if you taught a child about symmetry, you would get similar results. You know? It would not be concerned about compositions, about the group structure. It would not be concerned about being exact. You would see lots of repetition here, lots here, and of a different kind. And here we'd see repetitions as well, not so clear, but some repetition. And that's, I think that's what this is telling us. So it's very good, but I think it's interesting. Now we wanted to do more than that. And this is a work in progress. And so what we want to do is, first is sort of a very simple toy example in 2D. And because we wanted to apply it to something completely different, paintings, we had to make the sacrifices of simplifying the problem a lot and doing this black or white contour. Now, we also want to do it for more complex, more physics, more data science problems. So in more than two variables, not just X and Y, not just an image. We will talk about this. Gabriel started working on that. We also, have questions. Like one you can ask is, because we threw a lot of information and we projected onto 2 dimensions, we haven't singled out the neuron that might have information of which symmetry is there. Is there a neuron that encodes a symmetry? Could be. Or neurons that encode other human interpretable quantities, so quantities that we would understand. Now it's all part of opening the black box and understanding what is happening in there. And so first, for the first question, there's there's 2 limitations, if you want, that we want to remove. One, because we studied paintings, we invented this decoy task that is very contrived and very limiting and throws out a lot of information, throws away a lot of information. And the second is that we did it by training 1 neural network for each potential. So because we started with 1,000 potentials, we trained 1,000 neural networks. It's not that it takes time, but then they're different, separate neural networks. And you see that each time we run it, we get slightly different results. So the first limitation, this decoy task. So if we don't want to study paintings, we don't have to do that. In fact, we can get rid of the contours completely and try to reproduce the full potential. So switch from classification to regression. And that's what Gabriel and our master students been doing. And then you gain a lot of accuracy. On 5 classes, you get it right about 95% of the time, I think is what Gabriel got. So this is getting better, and that makes sense. You have much more information to work with. And now once it's a regression, it's much easier to generalize, well, it seems much easier anyway, to generalize it to more than 2 dimensions. So that's the next step, one of the next steps. The second limitation is this thing I said, we're training 1 neural network for each potential. So we can't really single out the neuron that has information of what symmetry there is, because we can't match neurons across neural nets. Each time we train, we start from scratch, and even if there was 1 neural network, 1 neuron that had all the information about symmetry, in one case it's the first one, in another case it would be the last one, in another case it would be the middle. So we can't follow it from neural net to neural net. So one way to do it is to train a single neural net to produce all the potential. And that you can do using, for instance, a variational autoencoder, so unsupervised problem for those who. And there you have the same neural net to deal with all the shapes you've given it, and you can ask it which of the neurons holds information about the symmetry. We didn't actually do that. We actually jumped into yet another problem related to art. Rather than paintings, we wanted to look at music. The reason is that we don't even have to train our own variational autoencoder there. Google has already done it for us. There's so I'm not defining what a variational autoencoder is. It's a network that tries to reproduce all the inputs you give it again, a bit like we were doing, but the same network is trying to find a way to reproduce all the sorts of inputs that you give it. And instead of giving individual points and reconstituting all the points in the 3D image, the whole network reproduces all the images. If you did one whole image, then it will output something very similar to that image. The point of it is it's the same single neural net that can hold information about 1 million of songs here. And about songs, instead of asking for symmetry, we ask about other interpretable quantities, other quantities that we would define and that people have defined to quantify music. And actually you find, if you do it, what we're finding is that there is one neuron that holds most of the information about rhythm, another one that holds most of the information about pitch, another one that holds most of the information about melody. That's for music that is just short 2 bars of music, so up to 32 notes of music. If you make the piece of music that you're looking at longer, like 16 bars, which is hundreds of notes, then you need a couple of neurons to encode the rhythm, a couple to encode the pitch, a couple to encode the melody. But the point is that in each of these cases, we find that the information that we intuitively would want to use to describe quantitatively the data is also used by the network. The neural net puts in one neuron that same information. And that's an interesting point. And I think there's been research in this, when various people have done research in that, where they find that one single neuron holds very high level, very complex information that we can interpret. So it's not a black box completely. If you actually look into it, you find individual neurons that do the job that you would have done. For instance, in image classification, they find that there's one, I always give this example, there's one neuron that if you remove it, then the network stops recognizing ski results. So there's the ski result neuron. Here there's the rhythm neuron. So all of this. There's also people who've used it to try to solve physics problems. And they find that when they look at data from planetary motion, there's one neuron that encodes angular momentum. So all these physical quantities that we, as physicists, would define as very useful intermediates to solve the problem, to compute things, the neuron does this. Somewhere in its layers, and in particular in the unsupervised case, for those who understand who know what a variational automata is, it's exactly in the latent state that you find some information. There is one neuron there, exactly in the layer that encodes information that holds the information about one quantity that you as a physicist would probably have started using as well. So I would guess the conclusion for me is that this is not so much a black box. If you start looking into it, you get some understanding. And hopefully we'll continue. And as I said before, Gabriel here is still working with us on some of this. Here, we're possibly doing more dimensions and using it in practical problems. That's it. Thank you.
Thanks, Johannes, for this incredibly interactive and pedagogical talk. Is there any question here in the room, or at Zoom, if you can hear us still?
Sí, tranquilo que se escucha todo.
Okay. Any question at all?
Yeah. Actually, that's one thing we've looked at as well. So we used, because we wanted to save time and not train our own neural net on a problem, we wanted to look at music anyway, initially for symmetry. But it turns out that the logic we were doing, because we started looking at symmetry, I think applied to music, it makes more sense to look at parameters that people have already defined when they study music. So we wanted to look at this, and when you take a pre-built autoencoder built by Google, trained on millions of songs, they build a very, very large thing. I think the important parameter here is really not so much how many parameters, but how many dimensions it has. Rather than the 200 I mentioned before, that's 512 per power. So the first thing we found is that we don't actually need this 512. You only need 40. And if you do the counting of how many possibilities of arrangements of notes in 2 bars of music, it makes sense. Now, within these 40, parameters, or not parameters, dimensions of variables to describe independent pieces of music, we find that there are actually three that are particularly important and that correspond to these quantities that people have already defined when they analyze music independently of neural networks. So the neural network automatically chooses to use similar variables as people have used. And that's, so we've already gone down from 500 to only 40 we really need. Now we're getting down to about 3 or maybe 6 if you ask about a long piece of music. So I'm sure that answers your question. If I were to build myself this, I would build a smaller neural net probably. I would restrict it already to not 500 dimensions in this layer, in this intermediate layer, but just about 40. And maybe try to do less. But yes, the network is huge, and training it is very costly in computer time. That's why we didn't want to do it ourselves. But one possibility would be to apply the same logic back again now to the paintings. Because there we can choose the resolution. Not the paintings, but sorry, the potential. And here we could ask, is there a neuron that tells us about symmetry? So we kind of jumped off to the music thing because there was already a pre-trained model, and now we can maybe train ours for the potential. And that gives us an idea of how complex we might need it also. I don't know if that answers.
So there is a question on Zoom. Someone raised their hands. Judita, please, you can.
Hi. Yes. Hi. Thank you very much for this very clear and very nice talk and super nice analysis. So maybe you already answered in your talk, but maybe I missed it. So I have a question. So does the frame or the subset of the painting affects the results? So did you try different? So that did you try like subsets of the picture? So does it affect the result of the check on the symmetry?
Okay, I guess. Show my face. So we actually trained the whole thing on potentials. It only sees paintings in the, if you want, it's in the test set. When we train it, it never sees any painting. It only sees these very crude, simple drawings that are potentials. So these circles, these lines, and wiggly lines. And then once it's trained on that, we test it against other potentials. That's why it does 73% of the time, which is decent. Can be increased if we don't use controls. So we understand that. But we wanted this crude depiction of images, of control lines, to apply it to paintings. But it's never seen paintings at that stage. So we chose paintings, famous paintings, and we applied it to that. When we show the results that are interesting, now we could apply it to other paintings. And we did that. And in general, the features that I described come back again. Cubist paintings will give you a high chance of discrete translation for the reasons I explained, because there are repeated patterns there. And paintings that depict a face or a human usually give you some degree of discrete reflection, so along the median axis of the person. So what you expect, and again, thinking always that this is a rather intuitive, not crude, but intuitive picture of what symmetries are. So I guess it doesn't, in a sense, it doesn't really depend on the paintings you choose, because you can always look at more and more paintings.
But my question is, so for example, in some paintings you have a region which is has some symmetry, while the rest maybe not. And so does it find the interesting region and gives you a high result? So maybe that part of the painting is highly symmetric, while the rest is not. Will the result be on the whole painting, and then it will not be such a strong symmetry? Or
yes, exactly. You're right. So if you zoomed in on, let's say, the Kandinsky painting.
So you have to zoom it, right? So you have to kind of have a bit pre-knowledge to find the region.
In what we didn't zoom it. We gave it the whole painting. Now, if you wanted, let's say, it finds in the Kandinsky studies in color, I don't remember the name. I can show it again, maybe. The one I showed most often. Yeah, So the top left one here. So it finds discrete translations, so repeated patterns. Remember, it doesn't see the colors. We've removed the colors. We just look at the shapes. So it sees repeated circles and repeated squares, I guess. Now, we did this as well. We said, well, what if we zoomed in on just this square? What does it see? Then it starts giving more weight to rotation invariance. Yes, we can look. So it does look at the whole image. And if we select just one part and define that as the whole image again, then it will give a different result because it looks at the symmetry just within that dimension. It's within that domain.
Yeah. Okay. Yeah, it's very interesting. It's very interesting.
Thank you.
Yeah. Well, yeah. Thank you very much. So it's a super nice study.
Thank you.
You have a question here, please?
Predict what the arcs of
I don't think
Could you repeat the question for Zoom?
Oh, yeah.
Sorry,
Somebody's asking if we could use this approach to fill in gaps, let's say, to reconstitute the arms of the Venus of Milo. So there are some Greek paintings, some Greek sculptures where parts are missing and reinvent them, extrapolate. I think people can do this. That's not the way I would do it, but people use unsupervised generative AI. So not variational autoencoders, but something that is harder to train, but a bit more realistic. They're called GANs, generative adversarial networks. And then within this, I think you can extend, you can introduce other angles of view, and you can extend. So there's ways to do it. That's not the way I would do it. Most people have done exactly that. But I'd be surprised if you were but this is more about understanding specific aspects of the inner workings than about extending the possibilities of AI. So I think the answer is what you say can be done, I would guess. It might even have been done, I don't know. And the way I would think is using something called GAN, GAN.
Okay. Is there any other question on Zoom? Yeah, probably not. So we'll leave it here. And thanks again, Johannes, for this amazing talk.